Hello, my name is Casson, and in this presentation I'm going to present our work on flexible devices for non-invasive brain monitoring. So we're looking to introduce really two contributions in this work. One on the printed and the flexible sensors themselves, but then also using those to introduce application level novelty and do sensing that hasn't previously been possible. The application in this case is known as EEG, and I'll start off by introducing that, some of its limitations, and then loop back to talk about our printer-based approaches, the novel electrodes that we've made here, and then I'll present the performance characterization of those electrodes and their use in the application. The EEG is a widely used, non-invasive brain monitoring approach. It's based upon putting small metal electrodes on the head, making contact not with the hair, but with the scalp itself. And you can use that to measure outside of the body the small electrical potentials that arise due to the operation of the brain inside the body. It's a very widely used modality for epilepsy diagnosis and for sleep disorder diagnosis. And in principle, it's portable. The electrodes and the instrumentation can be miniaturized, and you can take them out of the clinic, out of the lab, and do in the wild experiments. In practice, though, EEG has a number of limitations. So principally, you need to put electrodes all over the head, and that means it's not very miniaturized, it's not very socially discreet if you wanted to walk down the street wearing a unit. But also, we need to make a good contact with the scalp, and so to do that between a rigid metal electrode and the scalp, we use a conductive gel. And there's an example of that in the bottom right hand side of the screen here. And that gel is just a bit of a pain because it's messy to set up, it's difficult to set up, and it also dries out over time, which limits the potential recording duration. So in recent years, to overcome these limitations of EEG monitoring, there's been a big drive towards what's called wearable EEG and enabling in the wild EEG recordings in naturalistic situations. One of the key drivers in that has been a move away from putting electrodes all over the head to placing them behind the ear. And if you want to hear about the details of this, actually we're organising a mini symposium at the IEEE EMBC conference, which is running at the same time as this printed and flexible electronics conference. Broadly, the idea of behind the ear EEG is that there's no hair behind the ear, and so the electrodes can be easier to set up, easier to make a direct contact with the person's scalp. They're also intrinsically miniaturized and socially acceptable. You don't need electrodes everywhere, and people are used to seeing headphones and hearing aids in the behind the ear location. The challenge tends to be that you can't necessarily record everything that you're used to recording because you only have electrodes in some parts of the head rather than everywhere. But moreover, the challenge is that the EEG signals get very small. Generally, the further apart you put your electrodes, the bigger the signal that you will record. And so for ear EEG, what a lot of people will do is put electrode grids behind both ears. So they're physically separated, and it increases the size, the robustness of the signal to be collected. If you try to record behind just a single ear, the kind of same signals are there, but they're much reduced in amplitude, which makes them much more difficult to record. As a result, the research question that we're looking at in this current work is one of, can we use flexible and printed electronic structures to enable the recording of EEG components from behind only a single ear. So the signal that we want to record is very small, but what we know from existing literature is that the noise floor of an EEG electrode is inversely proportional to the contact area. So on the left hand side of the screen here, we've got a conventional rigid electrode made out of silver chloride, and we would use a conductive gel to help that make contact with the person. But clearly, as a bulk bit of rigid metal, it's not going to make a very good connection to a person. In contrast, on the right hand side, I flipped forwards to the inkjet printed electrodes that we made in this work, and we can see that it gets a much better contact to the person, and as a result should enable a smaller noise floor, giving us a better chance of recording these very small EEG components. Before I go into those electrodes themselves, just a few words about printing of electrodes for EEG, because we've looked at a number of different approaches for doing this in recent years. So we started off by looking at 3D printing of electrodes. If we're looking to put electrodes all over the head, hair is the big challenge. We want to make contact with the scalp, not with the hair. And so the approach for that is to use fingered electrodes. And they've got multiple prongs that hopefully kind of push past the hair and make contact directly with the scalp. And when doing that, there's a wide number of different degrees of freedom. So you can change the length of the electrodes, the number of fingers, how rounded they are on the tip. And that starts to let us personalise the electrodes, so we can get the best connection for different people or different parts of the head. So a number of years ago now, we showed we could 3D print electrodes using a rigid substrate. And then more recently, we've shown that we can 3D print a flexible substrate. And these are coated in silver chloride, so the sensing material is exactly the same as if you're using one of those bulk metal rigid electrodes. But now they're flexible, so you can push them against a person and it's more comfortable. They're fingered, and so they stand a better chance of making contact with the scalp rather than with hair. And we can start to look at how can we personalise them. For behind the ear electrodes, we don't have the issue of hair in the same way. And so rather than looking at 3D printing, we've been investigating inkjet printing. And we look at inkjet printing because we can do that onto temperature 2 paper substrates. So these are very thin and they conform to the surface of the skin very, very well. And it gives us an epidermal or a conformal sensor. So we've printed a silver ink using a Dymatics printer, and then we put an adhesive layer all of the way underneath the electrode. And this is really useful in two different ways. So firstly, it means that we're getting a very good connection to the body. We've seen that on the previous slide, and we've got the illustration of a body contact on this slide as well. What it also means is that we're maximising our sensing area. So in panel A on the slide here, on the left there's one of our printed electrodes on a tattoo paper substrate, and then in the middle there's a conventional electrode. This one's actually for the chest monitoring rather than the head, but it's the same principle. And the actual sensing area is just a small circle in the middle. All of the white circle around the outside is just adhesive. And so actually a lot of the total area of the electrode isn't being used for the sensing that we want to do. In contrast, our adhesive layer goes all the way under the electrode, and so the electrode is sized to the adhesion. And we're using all of the available space that we have to do sensing. And again, that should help decrease the noise floor, help us pick up very small signals. So we measured the performance of our electrodes electrically in terms of the resistance of the printed layer of the printed silver before we put the adhesion on, and that is robustly below about 5 ohms. The resistance of a connection to the body is about 100 kilo ohms or so, and so it's negligible in comparison. We also measure the capacitance by connecting the electrodes to a copper plate, and here we get about 10 nanofarads or so of capacitance. And that's about the same as the capacitive connection that we typically get when connecting to the body. And so it's not dominating, it's going to roughly halve the total capacitance that we get compared to conventional EEG electrode monitoring. To verify the functional performance of the electrodes, we recruited volunteers and put 2 electrodes behind a single ear. To give us a known signal to record, we showed a flashing light to our users. And what this produces in your brain is a response known as a steady state visual evoked potential. So if you flash a light at 10 Hertz, say, your EEG will have a peak in the frequency domain, in the power spectrum, at 10 Hertz. And this is the basis of many brain-computer interfaces. You can imagine if you've got a screen with lights in different corners flashing at different frequencies, you can look at the EEG to see what the dominant power frequency is, and from that determine which of the different squares the person is looking at. So on the graph here, we've got power spectrums for when we flash the light at 7 Hertz and for when we flash the light at 10 Hertz. And we can see the expected peaks. We can also see a first harmonic of that stimulation frequency. And that's exactly what we would expect from EEG theory. Compared to when there's no stimulation present, in the no stimulation case, we don't see the peak, which again is exactly what we would expect. Comparing the difference between those 2 traces, we can measure the signal to noise ratio, and doing this over all of the different recordings that we did give us an SNR of about 10 dB or so, so a good level of detectability. We also repeated the test, but with just conventional pre-gelled electrodes stuck on behind the ear, and there we can see that the height of the peak we measure in the frequency domain is exactly the same using the 2 different types of electrodes. So that's a very promising result. With our electrodes we see possibly less high frequency noise, but possibly slightly more low frequency noise. What we also find is that all of these are very sensitive to external interferers. So things like motion, things like moving the head, and so on. So the long-term direction that we want to move in is very much one of taking these technologies out of the lab, enabling socially discrete monitoring. What we've shown in this work is that it's fundamentally possible to measure these SSVP brain components from behind a single ear, but they are still very contaminated by motion and other artifacts, and there's a range of work to do before we can do robust monitoring. And that is what I was looking to go over in this presentation, bringing together our track record in printed electrodes and demonstrating that we can use those to enable EEG monitoring in ways that haven't quite been possible before. If you would like to send any questions or comments, my contact details are on the slide here. Please do feel free to get in touch.